So, welcome to the last lap of this course, the last topic that we are going to cover, which is that of constraint processing, also known as constraint satisfaction problem. So, there are a couple of objectives I have in covering this. One is of course to introduce you to this very generic, very general way of solving problems, but also to illustrate that this subsumes search and it also subsumes reasoning at the same time. So, you can do a combination of search and reasoning in constraint processing. So, in that sense it is quite powerful. So, we have been talking about these two aspects. We have not discussed so much on reasoning. If you have done a course on knowledge representation, then you would know what reasoning is about. We did mention it very briefly. Search, as we have seen, can be state space or solution space. We saw planning problems, configuration problems. We saw satisfaction and optimal solutions, for example, the SAT problem and the TSP problem. And we said that we will solve these problems by searching, which means basically by trial and error. Then there is another aspect of problem solving, which is reasoning or logical deduction and things like that, in which there are notions of entailment and proof, and we draw inferences from what we know. So, this diagram we had briefly seen earlier. In the circle on the bottom here is the knowledge base, and each square is a sentence which can be true or false, and on the right there is a proof tree which eventually proves some formula alpha essentially, and we had briefly touched upon that, and we had said that the algorithms for finding proofs are essentially search algorithms. Now, we are looking at this unifying formalism, which is constraint satisfaction problems, that allow a large class of problems to be represented in a uniform manner, and that allows both search methods as well as reasoning to be used for problem solving essentially. So, the nice thing about whatever methods we are studying is that they are general purpose methods essentially. So, you represent them in a uniform manner, whatever you are doing, and then use general solvers to solve those problems essentially. As we will see today, that search and reasoning can be interleaved. When you are working with general solvers, then the end user has to only express the problem in the formalism that you are using for posing the problem. In our case, it is going to be a constraint satisfaction problem, or CSP as we call them, and then some off the shelf solver can be used to solve it essentially. So, a little bit of mathematical background about relations, which I am sure you are familiar with. A mathematical relations on a set of variables is a subset of the cross product of the variables essentially. So, brother, sister, aunt, all these are relations. Here there is a domain of 4 numbers 1, 4, 7, 9, and the relation we are trying to define is the less than relation. Now, what does D cross D mean? It is the cross product of the domain. That means all pairs 1 1, 1 4, 1 7, 1 9, 4 1, 4 4, 4 7, 4 9. So, like this there would be 16 elements in the set essentially, all pairs of elements. Some subset of that satisfies this relation called less than, and that is why we say that a relation is a subset of the cross product essentially. In the extension form, you can see that the subsets which satisfy this relation is, for example, 1 and 4, because 1 is less than 4, and 1 and 7, and likewise 4 and 7, and all the things which are this. This form of representing it as a set is known as the extension form, and we will essentially try to use them in our algorithms. Mathematicians would typically use an intension form, which means you describe the set in some way, and that description is that it is a set of all pairs x and y such that x belongs to D and y belongs to D, and x is less than y essentially. So, we are using the mathematical ordering less than in the description of the relation. Supposing you have a domain of courses. So, let us say we are talking about 3 courses here. So, this is the domain of courses and it has got 3 courses AI and DBMS and ML, let us say, and there is a domain of rooms. So, let us say again there are 3 rooms, this thing. So, we can define a relation as to which course is being taught in which room. Let us call it course room for want of a better word, and this subset of the cross product of these two things. So, AI could have been taught in 24, 26, 36, DBMS could have been taught in 24, 26, 36, likewise ML could have been taught in 24, 26, 36. What this relation that we have shown is only talking about AI and DBMS. It is saying AI is taught in 26 and DBMS is taught in 24. So, it is basically capturing the relation between courses and the rooms they are taught in. The most familiar relations that we are comfortable with are human relations. So, let us say the domain is 4 people, Amy, Arun, Anil and Aisha, and we can define a relation called aunt. So, sometimes we write the arity of the relation. It says it is a relation between 2 elements in this thing. So, what we have shown here in red is that Aisha is the aunt of Amy and Arun as well as Anil essentially. Then we can have a brother relation, and in the brother relation we have said Arun is the brother of Amy, Anil is the brother of Arun and Arun is also the brother of Anil essentially. You could define a siblings relation which would have arity 3, which means there are 3 elements in this every tuple. So, it is a tuple of 3 elements. So, it is a subset of D cross D cross D essentially, and the various permutations that could be used to describe this 3 siblings. Relations, as you would know, they form the basis of predicate logic. So, when you say that for example, brother, let me just use B for brother, and I say let us say Amy and Arun is true. That is what we mean by predicate, sentences which are true or false. Then we can define the semantics of this relation by saying that this pair of Amy and Arun must belong to the brother relation, which is of course indeed the case, because as you can see here this pair is there in the relation, and the semantics of first order logic or logic in general is defined in terms of relations. So, in the language we say brother Amy Arun is a predicate, but its semantics says that the pair of Amy and Arun must belong to the brother relationship. So, essentially a predicate corresponds to a relation, and that is why we say that relations form the basis of predicate logic. Now, let us come to constraint satisfaction problems. A constraint satisfaction problem is defined as a triple of 3 elements x, or 3 sets you can say x, d and c. It is also called a constraint network or sometimes simply a network R essentially. So, there is a nice book by Lena Dechter called Constraint Processing, who often uses this notation of a network R in her book essentially. So, constraint satisfaction problem is basically a triple and we sometimes call it as a network. What are x, d and c? X is a set of variable names essentially. So, for example, we had some examples of courses and rooms and so on, or whatever the case may be. D is a set of domains and one for each variable. If there are n variables in x, then we need to define d domains, one for each essentially. So, what is a domain? Domain is a set of values that variable can take essentially. We will confine ourselves to discrete finite domains, which basically means we will not talk about real numbers and things like that essentially. And finally, C is a set of relations or constraints. So, C stands for constraints on subsets of variables essentially. So, we have seen, for example, brother was a subset of arity 2, siblings for the subset of D cross D cross D it is. So, basically the subset on which that relation is defined is called the scope of the relation, and we will often use S to stand for that. What we are going to study here in this next few lectures is basically a preview of a course that I also teach called AI constraint satisfaction problems. So, we are going to focus on finite domain networks. That means what? The domains are going to be finite essentially. Can be represented in extensional form, and that is what I had mentioned also, that we will often use that essentially. So, let us say that for some reason you have defined these variables as course, slot, room and faculty essentially. And then of course, you will have to define a domain for each of them. So, domain of course, domain of slot, domain of room and domain of faculty. So, let us say the domain of course has 4 courses AI, DBMS, ML and PL. There are let us say all these 7 slots A, B, C, D, E, F, G. There are 4 rooms 24, 26, 34, 36 and the faculty, let us say there are 5 of us essentially here. We can define binary constraint networks. What do we mean by binary constraint networks? Which are constraints between 2 variables essentially. So, we can define relation between courses and faculty. So, we are saying here for example, that AI is taught by DK, not mentioned in the list, but discrete mathematics is taught by JS and so on and so forth. We can define that these are the people who teach these courses essentially. Likewise we can define a relation between courses and rooms. So, we can say AI is taught in CS 24, discrete maths is taught in CS 34 and so on essentially. We can also define the relation between courses and slots, that AI is taught in C slot, DM is taught in D slot and so on and so forth. And finally, we can also have a relation between faculty and slots, that these faculty are teaching in these slots essentially. That is how students often tend to talk about courses. So, there are these 4 different relations. We can have other constraints. So, we can say for example, a faculty should not have 2 consecutive slots because they do not like teaching like that, which basically means that if a faculty is teaching 2 courses, they must not be slotted in consecutive slots. These are the kind of problems that people who create timetables for courses have to deal with. But in general, what is a solution? A solution of a CSP is an assignment of values for all the variables such that all the constraints are satisfied. What are the constraints? We illustrated 4 constraints between faculty and slots, faculty and courses and so on and so forth. And every element in this was an allowed thing. So, for example, MK can teach in slot D essentially. So, this is the constraint is an extension form essentially. So, a solution to a CSP is a assignment to all the variables such that all the constraints are satisfied. So, for this previous example, this could be an assignment which says the course that we are talking about is AI, slot is C, room is 26, faculty is DK. So, the solution is one course and its allocation essentially, and this is the way that we have formulated this problem. Perhaps you would like to try a different formulation essentially. But more generally, a network or a CSP, we will use the term R for that, is said to express a solution relation. So, a solution relation is a relation on all the variables that are there in the CSP, all the X variables in X. So, in our example, it is a relation over all these 4 variables. We have a value for course, we have a value for S is for slot, C is for course, R is for room and F is for faculty. So, this should have been R. And the solution relation is a set of all possible solutions. What we have shown here is only one solution which talks about the AI course and C slot and CS26 and DK. Now, if you look at the course allocation problem in general, it is a little bit more complex than this. So, just we will touch upon it in the passing to just to illustrate that there are complex problems that occur. So, now we have said that each course is a variable. So, that means you have to assign a value to that essentially. What will be the value? The domain of the variables would be, for example, the faculty members who teach that course essentially. So, the domain of AI, for example, may be these 3 faculty members who can teach that course, and likewise for the domain of every other course that we have mentioned here. We have mentioned 4 courses: AI, database management systems, machine learning and discrete maths essentially. So, these are the domains essentially. Then the constraints can be between 2 courses. So, 2 variables. Remember that constraints are always between variables. So, the 2 variables that we are talking about here is AI and ML, or they can be between DBMS or ML essentially. What? So, we can say that okay, AI is taught by DK and ML is taught by JS essentially, and likewise this thing. Likewise for DBMS we can say the DBMS is taught for by JS and ML is taught by RR essentially. So, we basically pairs of things. We are just trying to see how constraints are represented. We have not spoken about slots, rooms and clashes here. And we will just come to that in a moment, I think. There is sometimes we use a constraint called all different, which means that all the variables must get unique values. So, if you wanted to say that one faculty member can teach only one course, then we have 4 courses, and if we just say all different, that means that the solution to them will have different faculty member for each course. Remember that in our representation here, courses are variables, there are 4 courses. So, as an exercise, I will ask you to represent the all different relation in extensional form, let us say for these 4 variables. So, coming to courses, slots and timetables. So, look at the course allocation problem that one faces. Given a set of courses and we have relations between courses and teachers, who teaches what, relation between courses and batches, who can register for the course, between slots, courses and batches, so that there are no clashes, between faculty slots and slots, so there are no consecutive slots, for example, we have said, or courses, slots and rooms, so that there are no clashes. So, basically you have to assign courses to faculty, or you have to assign rooms to courses, and you have to say who can register for the course and everything, so that there is no clash essentially. So, the task is to do course allocation, who is teaching what, and also the slot and the room timetabling essentially, and it is a pretty tough problem, so much so that there is a separate conference on timetabling essentially only, and people are still working on it. So, apart from the constraints mentioned above, there can be additional constraints. So, for example, one can say that DK will teach AI and DBMS must be in C slot. So, you can say that we are specifying part of the solution already, that the solution must have this relations, and the rest you find so that there are no clashes essentially. But that's quite a difficult problem. So, we will leave that alone and start with simpler problems. We had mentioned the map coloring problem earlier. So, there are these 5 regions A, B, C, D, E, and the task is to color them with a different color, like we do if you have seen a school atlas, a political map and things like that. We have also stated that every region has a preferred set of colors. So, as you can see on the figure on the right, A has the set B and G, which stands for blue and green essentially. we are represented this problem as a constraint graph. Every constraint satisfaction problem can be represented as a constraint graph, and the constraint graph basically looks at the variables. There are 5 variables A, B, C, D and E. Their domains are the colors that you can use to color them, and the constraint graph captures the relation as to which variable is related to which other variable. And what do we mean by related in our example here? If two regions have a common boundary, then they are related. So, A is related to B, as you can see, and B is related to C, and B is also touching D and C at the same time. We can represent a constraint satisfaction problem. We always have a corresponding constraint graph essentially. What is a edge? The edge represents the relation between those two variables. And what is the relation? The relation is that they are not equal, that if A is equal to B, then B cannot be B essentially. So, that is of course the map coloring problem. We also sometimes use something called a matching diagram. So, a matching diagram is also a graph where we have all the 5 variables again represented here, but we have also the values in their domains represented inside some nodes, as you can see, or clustered together in some nodes. The graph is between the values essentially. And so, what does this edge represent? So, for example, if you can see there is an edge between B and R here. This R is for region B and this B is for region A, and there is an edge between B and R. It says that you are allowed to choose these two values, that you can choose blue for A and R for red. So, an edge in a matching diagram connects values from different variables which can be assigned the value together in the solution. So, in the solution, that is fine to say that A can get a value blue and B can get a value R. So, notice that between A and B, for example, there is no edge between G and G. Why is that? That is because it is a map coloring problem and you cannot give the same color to two touching regions. So, only those things that are allowed are present in the matching diagram. So, again you can see between E and D there is no edge between R and R. Why? Because they are touching each other. So, you can't say this is red and this is red, then you will not be able to distinguish between the two this thing. So, this is a matching diagram which we often use for analysis of constraint satisfaction problem. For regions that are not connected, which means in the constraint graph there is no edge, for example, between A and E or between E and C, there is no edge. That means you can use any combination of values for them, and that essentially corresponds to a universal relation, which basically means that you can choose any combination of the values that are allowed in that. So, there is no edge between let us say A and D. What does this mean? As far as the specification of the problem says, everything is allowed. B, so this is A and this is D. B is allowed with G, B is allowed with B, B is allowed with R, and likewise for G. G is allowed with G, G is allowed with B, and G is allowed with R. This is a universal relation. That means any element can be connected to any element essentially, and that is what we have said in the problem description. We have not said that what should be the color relation between regions A and D when they are not touching each other. Then we use a universal relation, and that is depicted by the fact that there is no edge between A and D, as you can see, and therefore, any combination is allowed as per the problem specification. What are the solutions to this problem? That is what we would expect our constraint satisfaction solver to do for us. So, we might say find a solution, and it will do some whatever processing it is doing and return to us a solution where this is the coloring that is done for this thing. We might even say, is there a coloring in which region B has the color blue, and then the algorithm should come back and say that no, there is no such coloring. What do you mean by that? That it will not satisfy the constraints that touching regions have different colors. Is there a coloring for which B is equal to G? Again the system should come back and say that no, essentially. You can say, is there a coloring in which A is G? Then it will produce another coloring which is possible. In fact, in this example, these are the only two colorings which are possible. So, next I just want to illustrate, yeah.
So, isn't B as blue possible?
Yeah, so we will come back to that. Let me just illustrate this algorithm which does the allocation. We have not discussed what is the algorithm. But to quickly answer your question, blue color for B is not possible because it is touching the region C, and C has only blue allowed. So, B cannot have blue allowed essentially. So, you can see here that B and C are contiguous regions, right. So, and C has only one choice, which is blue essentially. That means B cannot be blue essentially. See, C has only one choice in its domain.
I was looking at the domain for B and all, because all three.
Yeah, that's what has been stated in the problem. So, in the solution only these two combinations are allowed, and that is what we call as a solution relation. We use the term row essentially. The row contains these two tuples of 5 elements. A has a value blue, B has red, and so on and so forth. So, let us illustrate the fact that constraint satisfaction problems, they combine reasoning with search, and there is a algorithm called dynamic variable ordering which illustrates this, and it does both. It does search. Say the search algorithm may order the variables based on the size of their domain. And so, choose the variable for assigning a color. So, the search algorithm will say, let me try different colors for different regions, but in what order should you try the colors? Either you can fix it a priori, or you can use an algorithm like dynamic variable ordering, which says that choose the domains, choose the variables with the smallest domain first, because they have more constraints. So, for example, variable C, the only color you can assign to C is B essentially. So, choose that first. So, that is the heuristic that we are using, that based on the size of the domain you decide which variable you will give a value to, in general speaking. And the other thing you can do is propagation, or which is reasoning alongside essentially. So, let us see how dynamic variable ordering plus propagation, which is as we will see later called look ahead algorithms, will work. So, let us look at the size of the domains. A has size 2, B has size 3, D has size 3, and E and C have size 1. So, we should choose E or C first essentially. So, let us say we choose C first. There is only one value in its domain, which is blue, and we assign that, and the moment we assign that, we see that because C has a value blue, B cannot have a value blue, and likewise D cannot have a value blue, because they are touching regions essentially. So, you can see that the domain of B has now shrunk to R and G, which are the two remaining colors, and the domain of D has also shrunk to R and G, but we written it in the order written there, which is G and R. So, two things we have done. First, we chose C because it has a small domain, and in this case the size is 1 only, and so we have to assign that value to C. Any solution must have C as colored blue. So, we have done that, and then we did propagation, that because C is blue, B cannot be blue and D cannot be blue. So, we prune the domains of B and D essentially, and the pruned domains are shown here, that both have got red and green, which are allowed. Now, again we apply the same principle and choose variable E because it is got the smallest domain. So, E can only take the red color, and once we know that E is red, we know that the domain of D also we must remove red from there. So, it has shrunk to only one value by now essentially. So, we choose that because it has only one value, and that value is green, that is the only thing left for domain of D. The moment we do that, we know that green cannot be used for B essentially. So, we must remove it from the domain of B, and now domain of B is also a singleton set, which is R essentially. So, we assign that B gets the value R, and at this point only one variable is left, which is A, and if you look at this diagram, you can see that A can be either blue or green. So, in fact, this algorithm has produced the two solutions that we saw in the last uh, slide. These are the two solutions. Blue, B is always red, C is always blue, D is always green, E is always red. It is only A which can change either to blue or to green. But this is a very small problem. In general, constraint satisfaction problems have larger domains and things like that. So, this is just a recap of what we had discussed in the beginning sometime, that the problem of Sudoku allows you to do reasoning as well as search. So, what is the kind of reasoning you can do? You can say that 5 is already in row 1, so it cannot be in row 1 anywhere else essentially. So, you could have actually put crosses elsewhere also. Neither can 3 and 7 be in these 3 locations, because 3 and 7 also they are in row 1. So, we did this reasoning earlier, that we figured out that 5 can only be in this square which is shown, and this is the kind of reasoning that you can do. So, what we are trying to show is that both reasoning and search can be subsumed by constraint satisfaction, and we will see this as we go along essentially. A quick look at the 6 queens problem, or the n queens problem. You have to place n queens on n by n chessboard, in this case 6 queens on a 6 by 6 chessboard, so that no queen attacks any other queen. And these red arrows show that if there was a queen present in that location, which is C3, then it would attack all the squares which this arrow covers essentially. Now, one way to represent this problem is as a binary constraint network, that you put constraints between 2 queens at a time essentially. So, the 6 queen problem specifies constraints between any 2 queens if you represent it as a binary constraint network. How would you represent it? You would say that the relation between queen 1 and queen 2, so this is queen 1 and queen 2, is that if you place queen 1 in location A, you can place queen 2 in location C, that is allowed essentially. So, queen 1 is here and queen 2 is here, because they are not attacking each other. And likewise, we just list out all such allowed pairs of locations where queen 1 and queen 2 be played. Which are the queen 1? The queen 1 is a queen in the first row and queen 2 is a queen in the second row. So, in the first 2 rows, how can we place the queens? That is captured by R12 essentially. So, these are all the values, and you can fill in the blanks. I have left some these things here. Likewise, you decide for all pairs of queens. So, between queen 1 and queen 3, between queen 1 and queen 4, between queen 2 and queen 3, between queen 5 and queen 6, and so on essentially. And that is how you could represent the constraint satisfaction problem as a binary constraint network. Next, we will start looking at solutions. So, we will do that in the next session.